Greetings, physics enthusiasts. This is lesson 4 in Unit 1, AP Physics 1. And as you can see, I have your textbook here in front of me. I want to start by doing an example problem for you. There are several problems on these pages that are assigned for this week's work. One that is not assigned is number 28. And of course, it starts down here and finishes up here. So let's read the problem, and then I want to show you how we could go about solving this problem. If you have a hard time seeing this, I apologize, it's kind of small. It's on page 49 in your textbook. Two cars, number 28 down here, two cars are traveling along a straight line in the same direction. The lead car at 25 meters per second and the other car at 30 meters per second. 25 meters per second and 30 meters per second. Okay, now I'm going to zoom in a little bit on this second part now. And the second car at 30 meters per second. So the one in the back is going faster than the one in the front and catching up. At the moment that the cars are 40 meters apart, so when they're 40 meters apart, the lead driver applies the brakes, causing his car to have an acceleration of -2 meters per second squared. So the car in the front, which was going slower, 25 meters per second, is going to have an acceleration of -2. So that's the beginning. They're 40 meters apart, go. And then so a second after that, the speed will be 23 meters per second. A second later, the lead car's speed will be 21 meters per second. A second later, the lead car's speed will be 19 meters per second. I'm subtracting 2 meters per second from the speed each second. This is the way I think about what's going on before I even get to what are they asking me to figure out. How long does it take for the lead car to stop? Okay. And assuming that the chasing car, the one that's going 30 meters per second at the beginning, the chasing car also brakes, also slows down, also has a negative acceleration. At the same time as the lead car, what must be the chasing car's minimum negative acceleration so as to not hit the lead car? In other words, I said this one behind is catching the front car. I want them basically both to stop right next to each other, so that they don't bang into each other. I pretend that they just barely touch, and that's how I'm going to solve that. And how long does it take for the chasing car to stop? So 3 questions there. So what I'm going to do is I'm going to summarize what's going on in this problem with a diagram and with some numbers. So there is the car behind, and then there's the car in the front. And I'm drawing the car in the front with a velocity with a shorter arrow to indicate it's going slower and this one's going faster. What are those initial speeds? The lead car is going 25 meters per second. And the chasing car, the following car, the other car is going 30 meters per second. Those are our initial velocities. And then this one's going to travel some distance and stop. And this one's going to travel some distance and stop. And I don't want them to travel the same distance and stop. I want this one to travel farther, and I want them to stop right at the same place. Now, this problem says at the moment that the cars are 40 meters apart. So this distance is 40 meters. Does this seem to comport with your understanding of the problem as read? This might be a good time to pause the video and go back and read number 28 again and see if, in fact, it sounds like what it's talking about is what I drew. Then I could also say some pretty obvious things like this distance, 40, plus this distance equals this whole distance. Oh, yeah. I could also do some kinematics for this one. I've got distance traveled, initial speed, final speed, acceleration, and time. Ooh, look, and I wrote those 5 variables vertically, the way I said we should. And this one too. I can say the distance it traveled, the initial, the final, A, and t. And it seems like 30 meters per second is the initial velocity, and 25 is the initial velocity. And I think we both want them to stop here. So that's what I sometimes call a hidden given. It didn't say v final is 0 for both of them, but if they're stopping there, there's my hidden given. So I know v initial and v final. I know v initial and v final. All right, what else? Let's read the problem again. Two cars are traveling along a straight line in the same direction. The lead car at 25 meters per second and the other car at 30 meters per second. At the moment the cars are 40 meters apart, the lead driver applies the brakes, causing his car to have an acceleration of -2. I'd forgotten they told us that. There we go. So I have 1, 2, 3 numbers. Once I have 3 numbers, I can use kinematic equations to find the other 2. How long does it take for the lead car to stop? Ooh, how long does it take to stop? This is the answer to letter A. If I find this, I've answered question A. Question B, assuming the chasing car brakes at the same moment as the lead car, what must be the chasing car's minimum acceleration? All right, so I want to find this acceleration, and that's letter B. Now, once I find this distance, that's this, I'm going to call this x1, and I'm going to label it x1. I'm going to call this x2. Did these two, x1 and x2, have a relationship? Yes, they do. x2 plus 40 is x1. Do you see that? x2 plus 40 equals x1. This plus this equals this. That means instead of x2, I can write x1 minus 40. x1 minus 40. So if I find this, I'm done with letter A. If I find this, I subtract 40 from it, and then I can find letter B. And then letter C, how long does it take for the chasing car to stop? And that's letter C. Are you seeing how I did that? So see if that all makes sense. Maybe put it on pause, think through it. And then what I'm going to do, I'm going to change colors here because everything else is just a little bit of algebra. Which equation am I going to use to find t? Number I want the kinematic equation without x in it. Let me get out my notes from the last video. Remember when I drew those when I wrote down those 4 kinematic equations? And I said, this is the one that does not have x. So I'm going to write this equation. Oh, wait. No, that has x. This is the one circled in red is the one that does not have x. So I'm going to write that equation. V final equals V initial plus AT. Always write the equation first, then plug in the numbers. V final is 0. V initial is 30 plus A -2 times t. Solve that for t, and you're going to see that t is 15. 15 seconds. I'll let you do the algebra, but that's how we do it. How do I find x? Well, I can use any of these other equations. Not this one because it doesn't have x, but this one or this one or this one. This one looks the easiest to me. Maybe I should use it. So I'll write x equals 1/2 v initial plus v final times t. X is what I'm looking for. 1/2 v initial, 30 plus v final, 0 times t. Ooh, now I know that. 15. 1/2 of 30 is 15. 15 times 15 is it 225? What's 15 times 15?
The answer is 225.
225 meters. See, you don't even need a calculator when you have Siri. If this is 225 and this is 225 minus 40, 185. And now I have this number, this number, this number. I use one kinematic equation to find this, and that's the answer to B. One kinematic equation to find this, that's letter C. I'll do just one of them for you. I'll find A here. So I want the equation that has X, V initial, V final, and A. Which of these equations does not have T? It's this one. V final squared equals V initial squared plus 2AX. Write the equation first, then plug in the numbers. 0 squared is still 0. 25 squared is 625 plus 2A, 185. A equals 625 divided by, let's see, negative 625 over 2 times 185. And you can do that on your calculator or ask Siri for some help. 625. Oh, here, I'll prove it. I did 25 squared. 25 times 25 is 625. Make it negative. Divide by 2 and then divide by 185. And I got negative 1.7. A equals, or is approximately equal to, about negative 1.7. It's an acceleration, so I write meters per second squared. And this is easy to find because you have all the other three. So that was my example problem for you. What if you did not know how to do this? Well, if you did not know how to do this, this was problem 28. Oh, the book tells me it's from section 2.5. So I could go to the chapter summary. The summary begins here. And on the next page, the summary tells me, hey, for section 2.5, you should use, oh, look at that, the kinematic equations, which are the equations I used here. So use the chapter summary to figure out which equations to use. When you're using kinematic equations, step 1 is to write the kinematic variables vertically. Plug in the numbers that are given in the problem. Identify what they want you to find. Select a kinematic equation, plug in the numbers and solve. Select a kinematic equation, plug in and solve. Select a kinematic equation, plug in and solve. We're going to do that over and over. Is drawing a diagram required? It's almost always necessary to understand. There's these two cars and they travel and they travel and they stop, just barely not touching each other. Oh, look at that. They traveled 2 different distances. The distance they were apart, 40, plus the distance the slower one traveled equals the distance the faster one traveled. Oh, there we go. So I hope that helps you see how we can solve these problems. I'm going to clear my calculator and put it away. And then I'm going to take a quick peek at my notes. Right, I showed you how to use the variables, the 5 kinematic variables, and the 4 kinematic equations. Great. What I want to spend a little bit of time on now is deriving for you the other kinematic equations. Last time, I wrote all 4 kinematic equations, and I took this one that I circled, and I showed you where it came from. The definition of acceleration turned into V final equals V initial plus AT. Check, done. I want to now derive this one for you. X equals 1/2 V initial plus V final T. Where does that come from? Well, that's just an average. remember, if I want to find an average of two things, one way I can do that is I can take the first thing plus the second thing, add them together and divide by 2. If I want to have an average of three things, I can do x plus y plus z and divide by 3, right? And so on. So what I had here was I had an initial velocity and a final velocity. And if I want to find the average of those, I'm going to add them together and divide by 2. If I start with an initial velocity v initial and I end with a final velocity v final, a simple way of finding the average velocity, which I sometimes write as v bar, is initial velocity plus final velocity divided by 2. So there we go. If I'm traveling at a constant velocity, I can multiply that velocity by time and get distance. This is rate times time equals distance from junior high. If I'm not traveling at a constant velocity, which of these velocities would I multiply by time to get distance? The initial velocity or the final velocity? Well, actually, I would multiply the average velocity by time to get distance traveled. So instead of average velocity, I'm going to write v initial plus v final over 2. And I'm going to multiply that by t and get x. And then I'm just going to factor out this 1/2. 1/2 v initial plus v final times t equals x. And then I'm going to switch sides. X equals 1/2 v initial plus v final times t. Oh, and that is the equation I was aiming for. If I wanted to make this a 2-column proof with statements and reasons, this reason would be given. We learned this equation in junior high, rate times time equals distance. This reason would be substitution. I replaced the average with an average, the sum of the initial and the final values divided by 2. So that's a substitution. Then this was, I would say, factoring. I factored out the 2, right? It's kind of the, just if I went from this line to this line, it's distributive, right? 1/2 v initial plus 1/2 v final. So factoring. And then when I switch the left side and the right side, do you remember that from the last video? Do you remember what I called that? I called that the symmetric property of equality. If A equals B, then B equals A. I can switch the sides. That's called the symmetric property of equality. Right. All right. So that's how we derived this equation. Now I'm going to derive this one for you. I'm going to show you a method for that. And I'm going to let you use the same method to derive this one. Now, what is special about this equation? What's special and useful about it is that it does not contain v final. So sometimes letters are given and another letter is asked for. V final is neither given nor requested. So that is the utility, the usefulness of this equation. This equation has v final in it. This equation has v final in it. How could I use these two equations that have v final to get an equation that does not have v final? So what I'm going to do is I'm going to write down those two equations that I already derived for you. X equals 1/2 v initial plus v final times t. And the other equation is that does not have v final, right? That does have v final. V final equals v initial plus at. All right, I'm going to use these two to create this one. And since the goal is not to have v final around anymore, why don't I do a substitution? X equals 1/2 v initial plus v final times t. Now, did you notice that I said V final, but I did not write V final? And instead of V final, I'm going to write V initial plus AT. I did a substitution. X equals 1/2 V initial plus V final T. Instead of V final, I wrote the right side of the equation since the left side is V final. I wonder what's going to happen. X equals 1/2. V initial plus V initial is 2V initial plus AT times T. Now I'm going to distribute this 1/2. X equals 1/2 times 2 is 1. V initial. 1/2 times AT is 1/2 AT times T. Now I'm going to distribute the T. X equals V initial T plus 1/2 ATT is 1/2 ATT T squared. Oh, wait a minute. Doesn't that sound familiar? Yes, it does. It's this one. So now I've derived 3 of them for you. Where did this kinematic equation come from? It came from these other 2, but I eliminated V final. Very nice. So what is left for you to do on your own is to derive this final equation. What is special about it? What is useful about it? What is its utility is that it hath not, it contains not the letter T. So what I would do is go back to this equation and solve it for T. What does that mean when a math teacher says solve for T? It means rearrange so that instead of X being by itself, you get T by itself. So T is by itself, and then there's a bunch of other stuff on the other side. Also solve this one for T. So I would rearrange this one so it says T equals stuff. I would rearrange this one so it says T equals other stuff. And since T equals stuff, and here T equals other stuff, set stuff equal to other stuff, and rearrange, and what you gonna get? You know it, you're gonna get this one. Okay, so that'll take you 5 or 10 minutes to do that. But take these 2 equations, either solve this one for T and sub in here, or solve this one for T and sub in here, or do what I suggested, solve both for T. T equals stuff, do that algebra. T equals other stuff, do that algebra. And set stuff equal to other stuff. Rearrange, and you'll get the 4th kinematic equation. Ta-da! That is our video for this week. So it wasn't a whole lot of new information. I derived equations for you, and I showed you how to use the equations to solve problems. I talked a little about the 5 kinematic variables and writing them vertically. I talked about the 4 kinematic equations and writing one first, and then underneath it plugging in numbers and then solving. Great. I will see you soon in class. Have a great day.